Hello everyone. Today I am going to deliver a lecture on multiple linear regression model. It is a brief introduction to multiple linear regression model, and this lecture is based on the syllabus of BSc CBCS 4th semester statistics honors paper linear model taught in the colleges under Dibrugarh University. In multiple linear regression model, we attempt to predict a dependent or response variable y on the basis of an assumed linear relationship with several independent or predictor variables x1, x2 up to xk. In addition to constructing a model for prediction, we may assess the extent of the relationship between y and the x variables. The multiple linear regression model can be expressed as y is equal to beta naught plus beta 1x1 plus beta 2x2 plus beta k xk plus epsilon. Here we have to estimate beta parameters when the model is linear in betas but not the x. To estimate the betas in the above model, we take a sample of n observations on y and the associated x variables. Then the model for the ith observation becomes yi is equal to beta naught plus beta 1 xi1 plus beta 2 xi2 plus beta k xik plus epsilon I. Here I takes the values 1, 2, 3 up to n. The assumptions for epsilon I and yi are essentially the same as those for the simple linear regression model. They are expectation of epsilon I equal to 0 for all i's, or equivalently expectation yi is equal to beta naught plus beta 1 xi1 plus beta 2 xi2 up to beta k xik, and variance of epsilon I equal to sigma square for all I, or equivalently variance of yi is equal to sigma square. There is a constant variance for all yi. And covariance of epsilon I epsilon j equal to 0 for all I is not equal to 0, or equivalently covariance of yi yj is equal to 0, which means that the all y's are independent to each other. So assumption 1 states that the model is correct. In other words, that all relevant x's are included and the model is linear. Assumption 2 asserts that the variance of y is constant and therefore does not depend on the x's. Assumption 3 states that the y's are uncorrelated with each other, which usually holds in a random sample. When all three assumptions hold, the least squares estimators of the betas have been some good properties. So if one or more assumptions do not hold, the estimators may be poor. Now for each of the n sample observations, we have n equations like this. For the first observation, this is y1 is equal to beta naught plus beta 1 x11 plus beta 2 x12 plus beta k x1k plus epsilon 1. Similarly, for the second observation y2, and then for the nth observation, this is equal to beta naught plus beta 1 xn1 plus beta 2 xn2 plus beta k xnk plus epsilon n. So if all these n equations, if we write in a matrix form, then we have this type of expression. This is the y vector, y1, y2 up to yn. Then it is the x matrix. It is a n by k plus 1 matrix. Then the parameter vector, beta naught, beta 1 up to beta k. And this is the error vector, epsilon 1, epsilon 2 up to epsilon y. And in compact form, this is equal to y is equal to x beta plus epsilon. Here the matrix x is n by k plus 1, and n is always greater than equal to k plus 1. That is, number of observations should be always greater than the number of parameters. And rank of x is always k plus 1. And the x matrix is sometimes called the design matrix. So the previous three assumptions on epsilon I or yi can be expressed in terms of the matrix form also, and they are expectation of epsilon is equal to 0 or expectation of y equal to x beta. The covariance of epsilon equal to sigma square I or covariance of y is equal to sigma square I. So the assumption covariance of epsilon is equal to sigma square I includes both the previous assumptions, variance of epsilon I equal to sigma square and covariance of epsilon I epsilon j equal to 0. The assumption 2 can be expressed in other way also as covariance of epsilon is equal to sigma square I, which implies that expectation epsilon prime epsilon is equal to sigma square I. Since expectation epsilon is equal to 0 and expectation epsilon prime epsilon is a variance matrix, so from this assumption we have this variance covariance matrix like this. It is a n by n matrix. Here all the diagonal elements implies the variances and the off diagonal elements shows the covariances of all epsilons. Since the covariances are all 0 and the variances are all the constant variance of sigma square, so we have this type of matrix. So it is a double assumption. So each epsilon distribution has the same variance, which is referred to as homoscedasticity. All disturbances are pairwise uncorrelated. The beta parameters are called the regression coefficient. To emphasize their collective effect, they are sometimes referred to as partial regression coefficient. The word partial carries both a mathematical and a statistical meaning. Mathematically, the partial derivative of expectation y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus dot 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 beta k xk with respect to x1, for example, is beta 1. Thus, beta 1 indicates the change in expectation y with a unit increase in x1 when x1, x2 up to xk are held constant. Similarly, we can interpret for beta 1, beta 2, beta 3 up to beta k. And statistically, beta 1 shows that effect of x1 on expectation y if the other x's were not present in the model. Similarly, we can interpret for beta 2, beta 3 up to beta k statistically. So dear student, I conclude today's lecture here.